Hello, good morning. My name is Alana Menendez. I wish I could be with you all in person today. I'm a NOAA EPP, MSI scholar, and CESERT scholar, and PhD candidate at the City College of New York, where I'm advised by Dr. Maria Giorgio. And today I will be talking about colored dissolved organic matter in Long Island Sound estuary. So the Long Island Sound is a dynamic urban estuary with a storied water quality past. In 1990, the Long Island Sound even made the front cover of the New York Times for its pollution. And since then, there have been major investments in wastewater treatment technologies aimed at decreasing the amount of nitrogen and effluent released. But excess nitrogen still remains an issue in Long Island Sound. And so, for example, the New York City coastline is dotted with combined sewage outfalls. So during high precipitation, you could have release of raw sewage into the system. At the bottom right, we have a Long Island Sound report card from 2020. And we could see in this region of the Western Narrows, closest to New York City, the Long Island Sound receives a failing water quality grade. And this can be attributed to high concentrations of dissolved organic carbon, high concentrations of chlorophyll A that can lead to eutrophication, low summertime dissolved oxygen concentrations, low water clarity. And monitoring water quality is important because a lot of people use Long Island Sound as a resource, whether this is for fisheries or recreation. And having good water quality is important for equitable enjoyment across the whole sound and for use of this resource. And better data can lead to better water management. And so in addition to these anthropogenic gradients of Long Island Sound, we also have gradients of water quality due to freshwater inputs, which we just heard about in the previous presentation. And so to the eastern Long Island Sound, we have the Connecticut River mouth, which delivers 70% of fresh water to the Long Island Sound system. And with this fresh water, you have input of sediment, nutrients, color dissolved organic matter. Together, the Housatonic River with its mouth in the central Long Island Sound and the Connecticut River are responsible for 40% of nitrogen entering the system. And then these river inputs also affect metabolism of the system as a whole. So Vlahos and Whitney in 2017 saw that with the highest river discharge years, the system can act as net autotrophic, where it's delivering dissolved organic carbon to the mid-Atlantic bight. And then during its lowest river flow years, it can act as net heterotrophic, where it is importing dissolved organic carbon from the mid-Atlantic bight. And system-wide sampling in Long Island Sound didn't begin until 1991. So this is 1 year after that New York Times article. And this is done by the Connecticut Department of Energy and Environmental Protection, the CT DEEP. And this data set from the CT DEEP, their sampling locations are shown on the bottom left, are really important and have been used in many Long Island Sound publications. And so they sample across the sound once a month throughout the year and then biweekly in summer. But we wanted to complement their work with optical analysis of organic matter. And so we know that organic matter plays an important role in carbon cycling, nitrogen cycling, and hypoxia in Long Island Sound. But to date, there haven't been any synoptic studies on Long Island Sound colored dissolved organic matter composition. And so a bit more on this parameter of interest, colored dissolved organic matter. So dissolved organic matter is we're defining as the portion of material that passes through, or organic matter that passes through a 0.2 micron filter. And then colored dissolved organic matter is the portion of DOM that absorbs and fluoresces light. And these absorption and fluorescence properties are important because this allows for remote detection of colored dissolved organic. And the absorption and fluorescence can also reveal information on the source and the fate of the dissolved organic matter. And so a bit more on the sources. So colored dissolved organic matter can be entering Long Island Sound from these rivers and being attributed to upriver forested soils, from wetland soils. Colored dissolved organic matter can be produced within the marine realm from phytoplankton decomposition. Colored dissolved organic matter can be entering from wastewater sites. So there are a lot of different sources, and then potential fates can include remineralization to carbon dioxide from ultraviolet light photo bleaching or microbial degradation. It can be lost from the dissolved pool with flocculation, or it can be eventually exported to the continental shelf. And dissolved organic carbon is the carbon component of DOM. And so with this work, we really wanted to capture these diverse pools of color dissolved organic matter within Long Island Sound. And so sampling began in 2017 and it's continued to present. And we have over 650 unique samples of color dissolved organic matter and ancillary properties across the sound. And so we've sampled from west to east across these dynamic river to estuary transects throughout all seasons of the year. And then we've also had near shore sites that we focused on and wetland sites that we focused on as hotspots of colored dissolved organic matter in Long Island Sound. And here I'm showing west to east trends. So Western Narrows to Eastern Narrows, Western Basin, Central Basin, Eastern Basin. And up top, we have color dissolved organic matter absorption reference to 300 nanometers. And so this is a proxy for the amount of color dissolved organic matter in the system. And to the bottom, we have spectral slope of 275 to 295. And so the spectral slope can indicate origin of the color dissolved organic matter. So it's an indicator of the quality. So higher S275 to 295 indicates material that's of a more marine origin or material that had time to undergo more photo bleaching from UV light, sunlight. And we see a distinct difference between CDOM amount between the Western Narrows and Eastern Narrows. So these are both quite west in Long Island Sound. But it's important to see this distinction because we did see in water quality grades a difference between the Western Narrows and Eastern Narrows. But overall, in these main stem sites, the amount of CDOM hovers between around 2 and 5 per meter. This is an optical property. And the Central Basin and Eastern Basin, you'll see there are much more dynamic ranges of color dissolved organic matter absorption and S275 to 295. And this is because the Central Basin and Eastern Basin have a few things going on. First, they're receiving bodies for these two large rivers, the Housatonic and the Connecticut rivers, respectively. And then also they're closer to the continental shelf, so they can be receiving more marine water. So with the river water, it would have higher CDOM absorption and lower S275 to 295. And then the marine water coming in from the continental shelf would be reversed, where it would have lower CDOM absorption and higher S275 to 295. And then the other thing is that we do see some slight seasonality in S275 to 295 with higher S275 to 295, the spectral slope in the summertime. And this could be because of more marine production from phytoplankton during these times, or because you have more daylight hours. So you could have more photo bleaching of this material. And here now we're showing these same properties. So up top, CDOM absorption at 300 nanometers and spectral slope from 275 to 295. And this is comparing the Central Basin to the Housatonic River. So the Central Basin is the receiving body for the Housatonic River plume. And to the right, we have this mapped. And so the distinction between Housatonic River water and Central Basin water was done based on a salinity threshold of 21 PSU. And so rather than having a strict spatial demarcation, and this is because this zone is really dynamic. So depending on when you're sampling this region, you could have very different water that you're actually sampling. So during high tide, you're going to have estuary water from the Central Basin pushing up into the Housatonic River. And then during low tide, you're going to have this distinct plume of Housatonic River water that's entering Long Island Sound. And so we're also using satellite data to examine these river discharge amounts and better quantify these river plumes. This is one example of a satellite application here. And so this is looking at medium spatial resolution imagery. So monthly composites from Sentinel-3 ULCHI. So the top image has an image from January 2019, and the bottom image has an image from January 2017. And we see to the right that we had really different monthly mean discharges for these two Januaries. So the January 2019 was much wetter. And the January 2019 also has in situ data overplotted. And so this was using a pre-existing algorithm from Cow et al. 2018, but we are working on developing our own algorithms tuned for this area. But we can see that with this higher river discharge, you have higher CDOM amounts within the system, and this is attributed to this allochthonous material, this terrestrial material entering the sound. And so we can see here with this imagery, the influence of this river discharge on color dissolved organic matter in Long Island Sound. And here, so we're looking at the DOC specific CDOM absorption. So as I mentioned, dissolved organic carbon, or DOC, is the carbon component of dissolved organic matter. And so DOC specific CDOM absorption is CDOM absorption divided by DOC, and then it's plotted with a spectral slope from 275 to 295. And we have this relationship here colored by the different regions. And we could see that we have the river and marsh sites with the lower spectral slope from 275 to 295, and the DOC specific CDOM absorption here corresponds to more colored dissolved organic matter, more colored material. And so this is significant, and this relationship is significant because dissolved organic carbon is a biogeochemical parameter, and CDOM absorption and spectral slope are optical parameters that can be, and these optical parameters can be retrieved and estimated from satellite remote sensing reflectance. So this relationship will help us to retrieve dissolved organic carbon from these optical parameters that can be remotely sensed. And then I'm just going to touch on this here for time's sake, but we were also looking at the fluorescence of colored dissolved organic matter. And so we ran a parallel factor model on all of our samples. And this is decomposing the fluorescent components. And so our model revealed that there were 7 primary fluorescence components for this data set. And so each sample will have a mixture of these components, and these components correspond to the composition of color dissolved organic matter. And so components 1 through 4 would be more humic-like. So for example, component 1 and 2, we could attribute to very aromatic material that's very terrestrial. Component 3 is a ubiquitous signal that can be attributed to both marine and terrestrial sources. Component 4 is a marine humic-like fluorophore. And then 5, 6, and 7 are protein-like components. And so 5 is tryptophan-like, and 6 is tyrosine-like. So tyrosine-like would be more degraded peptide material. And so this is providing further information on the quality of organic matter. And we can see with these plots, so this is plotted with longitude in winter, summer, and fall. We tend to see, as you go east across the sound, more protein-like contributions. And we could attribute this to more phytoplankton contributions, or more in situ production within the marine realm. In summertime, we have overall higher protein-like contributions, closer to 40% across the whole sound, which we would also attribute to more in situ marine realm dissolved organic matter production. In the spring, we have pretty flat curves, so we don't see as much of this trend with increasing protein-like ratios as you move east. And this, we were thinking, is potentially because during spring you have the highest river discharge. So especially with the Connecticut River, you have consistently highest discharge in April. And so this could be because, in the spring you have a lot of this humic-like terrestrial material that's still entering Long Island Sound. And so what we're doing with this information is we've been using k-means clustering to look at the different sample compositions, so we can identify samples with different component compositions to have a framework to analyze this data set, because there is a lot of spatial and temporal heterogeneity. And so in conclusion, thank you for listening. So we're trying to not just characterize color dissolved organic matter in Long Island Sound, but really try to identify the environmental and biogeochemical factors that influence the amount and quality of color dissolved organic matter to better understand source and fate. And we're also trying to use this data set to make better algorithms for satellite remote sensing retrievals. So particularly using high spatial resolution satellite imagery, such as Sentinel-2 and Landsat 8 and 9, which could help us with the high spatial resolution to look at plumes in the dynamic river estuary continuums. So thank you for listening. And of course, I would like to thank all of the funding sources and NOAA assessor and all of the lab members I've worked with for this project, and then everyone who's helped facilitate field work. So thank you.